guys, so in this video we're going to be talking about polar and non-polar bonds. So before we get on to exactly what a polar and a non-polar bond is, just going to take you back a few steps, and we'll start off by looking at this chlorine molecule. So chlorine molecules, two chlorine atoms bonded covalently, so they have a shared pair of electrons. So if we go back to our notes, the covalent bond video, the covalent bond is a strong electrostatic attraction between a shared pair of electrons and the nucleus of the bonding atoms. So nucleus in the centre of each of these atoms, those electrons are basically being pulled towards the nucleus. Now we've got a chlorine molecule here, so we've got two chlorine atoms. Both chlorine atoms are going to be the same in terms of the strength of attraction and how they pull the electrons towards their nucleus. So just imagine this as a bit of a tug of war. Each of the chlorine atoms' nuclei are trying to kind of pull that shared pair of electrons towards each other. Because it's done by an equal amount, those shared pair of electrons sit in the middle of that covalent bond. Now, this is because those chlorine atoms are similar in terms of the strength of the attraction between the nucleus and that shared pair of electrons. Now, this isn't always the case. The electrons are not always shared equally. So we're going to have a look now at what affects how electrons are shared in a covalent bond. So we're going to look at something called electronegativity. So electronegativity is the power of an atom to attract the pair of electrons in a covalent bond. So let's have a look at this table that is currently on the board. So there's a couple of elements there, and the value beneath them is basically its electronegativity value. So the higher the number, the more power you have to attract a pair of electrons in a covalent bond. So basically, you're kind of the stronger end of that tug of war. So things like fluorine are really good at pulling those electrons towards each other, so they're the kind of the strong ones. Things down here like potassium are not so good at pulling the electrons towards each other. So you will notice as you go across the periods in the periodic table that electronegativity value increases. This is because as you go across the periodic table, you get a stronger nuclear attraction. In other words, the number of protons increases as you go across the group, same number of shells, so the nuclear attraction is stronger as you go across. So that power of that particular atom to attract the pair of electrons increases. And you'll also notice as you go down the periodic table, the electronegativity value decreases, and that's because you are increasing the number of shells. So there's more shells, therefore more shielding, so the nuclear attraction becomes less. So since electronegativity is the power of an atom to attract a pair of electrons in a covalent bond, and not all atoms have the same electronegativity, that means that depending on what atoms you have bonded together depends on how those electrons are distributed. So let's go back to that chlorine molecule now. So within that covalent bond, you've got two chlorine atoms. Both have the same electronegativity value. So there is no difference in electronegativity. They are both equal in attracting that shared pair of electrons, as we said before. So because there is no difference in electronegativity, those electrons sit nicely in the middle and are shared equally. And that is known as a non-polar bond. Electrons are shared pretty much equally. We have a non-polar covalent bond. Non-polar bonds don't always mean there is no difference in electronegativity. Sometimes just a small difference in electronegativity creates a non-polar covalent bond. An example that you will come across a lot is a carbon-hydrogen bond. So when you get onto the organic side of chemistry, you'll come across a carbon-hydrogen bond a lot. And although the carbon and the hydrogen don't have exactly the same electronegativity values, there is only a small difference between them, so they pretty much share their electrons evenly. So again, this carbon-hydrogen bond would be a non-polar bond because it is only a small difference in electronegativity. And the shared pair of electrons pretty much sits in the middle of that covalent bond. Okay, so let's have a look at what happens when we get a difference in electronegativity. So we're going to have a look at this carbon-oxygen bond, shared pair of electrons. So carbon had an electronegativity value of 2.5 and oxygen had one about 3.5. So there is a difference in that electronegativity between those two atoms, and it is significant enough that the electrons are not shared equally. So let's remember what electronegativity is. It is the power of an atom to attract a pair of electrons in a covalent bond. So oxygen has the higher number, so it has a greater power of attracting that pair of electrons, so the electrons actually sit a bit closer to the oxygen than they do the carbon. So the electrons are not shared equally within that bond. The oxygen is winning this tug of war and pulling those shared pair of electrons towards that particular atom. So what happens is you get this polar bond. So a polar bond is where the electrons are not shared evenly. That shared pair of electrons is not shared evenly. And what happens is you get a slightly negative side of the bond and a slightly positive side of the bond. So it's not like an ionic bond where you've got positive ions and negative ions and electrons are being transferred. The electrons are just slightly more towards the oxygen in this particular case. So because the electrons are negative and they're slightly more towards the oxygen, you get a slightly negative charge around the oxygen, and that is shown by this little delta and a minus that I've just put on the board, okay? And this is known as a partial charge. So the little delta kind of represents that it's a teeny tiny charge. So because the oxygen has this delta minus, the carbon is slightly positive because it's got electrons going away from it, so slightly positive. So those little delta things just mean that it's slightly charged, not a full-on charge like you get in ions. So if you have a polar bond, you'll have a slightly positive end and a slightly negative end. And again, this will affect its physical properties and its chemical properties, how it reacts, how its boiling points, things like that. So it's important that you're able to see the difference between a non-polar and a polar covalent bond. So if you have a really large difference in electronegativity, basically one of the atoms has got the strength to pull that bonding pair of electrons so far towards it, basically one of the atoms loses the electrons and the other one gains them. So it's that difference in electronegativity that tells us also if we have ionic bonds. So if we look at the example with sodium and chlorine, there is a large difference between their electronegativity values. So basically chlorine's electronegativity value is so much bigger than sodium's that chlorine, the chlorine atom, can actually pull those bonding pair of electrons towards it, so much so that chlorine gains the electrons and form a negative ion, and sodium has lost its electron and become a positive ion. So, in summary, you can pretty much have these three types of bonds depending on the difference in electronegativity between those two atoms. So at the top we've got a zero difference or a small difference in electronegativity, which means that shared pair of electrons sits between them nicely, and that is a non-polar molecule, or sorry, a non-polar bond. There's no charge on there because everything is, the electrons are in the middle, there's no uneven distribution of charge. Then we go down to the polar covalent bond, where you have a atom that has an atom that has a bigger electronegativity than the other. So we have a difference in electronegativity between them, and the electrons are unevenly shared. They go towards the more electronegative atom, and we get these partial charges. So we've got a little small minus charge and a small positive charge. Still a shared pair of electrons, but slightly uneven distribution, so we've got this slight charge on each of the atoms. And then finally your ionic bond, where one of the atoms, well, basically the difference between electronegativity between the two atoms is so great, one of them is much stronger than the other, so takes the electrons, has a full negative charge, the other one loses its electron and has a positive charge.